Then we have a change of basis. This is an important concept I want to go through. Change of basis. So let's think about basis first. So we have a vector space, let's say. Let's take an example. Let's say a car company produces some two kinds of cars. So there is something like a small car and there is something like a big car. So we need to know how many seats are there in the cars and how many windows are there in the car. So let's say small cars are 4-seater, large cars are 6-seaters, and small cars have 4 windows, large cars has 5 windows, something like that. Okay, so this is a very simple data. So now suppose I say I want some cars to carry some 20 number of people, and I can do different number of smalls and big cars for that, right?
Yes.
So let's say I have X number of small cars and Y number of big cars. So that means I need 4X plus 6Y equals 20.
Yeah.
Then I also need to know how many windows will be there, right?
Yes.
Total. Maybe I have to clean the windows or have to cut in some windows, something like that.
Or X.
So then number of windows will be 4X plus 5Y. And then you can calculate it and all that. And different values of X and Y, you can put it here to find the corresponding number of windows and all that. Now, let's say I, instead of like thinking of how many small cars and how many big cars, I directly convert the problem into seats and windows, like how many seats and how many windows. That makes any sense?
Okay, so 10, are you saying like 10x plus 9y or something?
Let me check it. So let's say I add the price column of the cars. Okay. Let's say small cars cost 80K and big cars cost 110K.
Okay.
Okay. So now, if I'm buying, let's say 3 small and 4 big cars, I can calculate 3 into 80 plus 4 into 110. And I'll get some number.
Yeah.
Make sense?
Yeah.
Now, instead of thinking of like cars charging us depending on small and big, can we think of cars charging us for seats and windows?
Yes.
So let's say I say that cars are charging us for 10K for every seat and 10K for every window. Then 4 seats and 4 windows will cost us 80.
Because
Makes
40
sense?
and 40, yes.
And 6 seats plus 5 windows will charge us 110.
Yes.
So you can pretend that charge is 10 for seat, 10 for window. Okay.
Yes.
So instead of thinking of how many small cars and how many big cars I need for say a particular group of people, I'm just thinking like, okay, so if I need 20 people, I definitely have charged 20 into 10 to 100 for the seat.
Yes.
And then I have to see how many windows I want. And accordingly, I'll be charged for the window.
Yes.
Okay. So I'm transforming a problem of how many small cars and big cars and things like that into a different coordinate, which is somewhat simplification for my thought because I am thinking in terms of seats directly, not how many small and big car I want. So I'm taking that part out easily. Okay. So this idea is like, this is not a very good example. This is just something easily I could
I was
think
about
of.
to say, I think the example maybe, but I understand where you're going with this.
You
We can
understand
think
the
about,
concept,
yeah,
like
the
you
framework.
change the, yeah, you change the coordinates in which you are working to make the problem simplified, and that has some natural meaning to you. Like
Yes.
the seat has a natural meaning to you. The
Yes.
small and big car may not be as natural for you. So we always try to transform our vectors in such a way such that they have some other meaning to me. For example, like let's say if I'm doing a linear regression data, I may have some meanings attached to say certain biometric data for some individuals.
Yes.
That has a meaning to me, or say even some sports data, I may have some special meanings like sports person will think in terms of this. But if you give some arbitrary column vectors or something, they may not think in terms of that.
Yes.
So we want to always transform those into this, whereas the actual calculation might be happening in some other coordinate space. So these transformations are always required. And these transformations again will be linear transformations, so they will involve a matrix.
Got it.
Okay.
Got it.
So in general, let's assume is the matrix of transformation. Okay.
Yes.
So whenever you had a vector x, that will become px. Okay.
Yes.
Now let's think of what will happen to our matrix A now. So let's say A was a matrix such that AX was Y. Okay.
Okay.
Now instead of X, I will write PX, and instead of Y, I have to write PY.
Yeah.
So let's say
A.
A becomes B, X becomes PX, Y becomes PY.
Yeah.
So then my equation will become, so first I will write A, which is B, times Px equals Py.
So we've changed our basis there.
Yes. Now there is a P here on the right hand side, so I would like to take that to the left hand side. So I will get P inverse P X equals Y. This is fine.
Yes.
I'm just taking P to the left hand side.
Yes.
Notice that the P sits on the left of the P. So it doesn't cancel with the P inverse doesn't cancel with the P because they sit on the other side. Okay. Now we started with Ax equals Y and we got P inverse BPX equals Y. And these two things are same. So we must have A equals P inverse B. Okay. So this is basically our formula for change of basis.
Oh.
Whenever you have a matrix in some one coordinate system and you want to transform to another coordinate system, and the change of basis is by higher P, so then the matrix also has to transform like this.
What was P again?
P is the transformation of the matrix.
Okay. Okay. Let P. Okay. Matrix. Okay. Gotcha.
Okay. So that is basically the seats and windows for every car, that data.
Okay. Got it. Got it.
Okay. And this is how formulas look like. Now, this is important because number one, as we discussed, like people think naturally in terms of certain vectors, certain features and all that. So we want to transform from that to the features that way, vice versa to whatever we are working with versus whatever we are expressing our results in.
Got it.
So like you will take the data, natural data, you will transform to a coordinate system which you are comfortable for the maths. And then the final answer, you will again transform back to those original natural coordinate system.
Okay.
Okay, and this is the transformation we have to use. That is first thing. And the second thing, the transformation is important because if say after choosing some suitable transformation, the matrix becomes easier to look at. So for example, the matrix becomes diagonal or something. Then that's very easy matrix to work with.
Right.
Okay. So
that's why we do the change of basis, you're saying then, right?
Yeah, that is why we will do
might
change of
allow
basis,
for a
because that new basis, even if it's not natural units that people would like to think of, That is going to make the math easy for me.
Yeah.
Okay? So we say that A and B are similar to each other. Similar is a technical term here, not English word. Okay.
Okay.
So whenever you see that the concept that matrix is similar to another matrix, this is what people mean.
Got it.
Second thing is, we say that a matrix is diagonalizable. It's similar to diagonal.